a modern GPU with the way. So, to begin with, I'm Yash. I am a fifth-year PhD student. My advisor is Professor David Cayley, sitting here. I completed my MS from Northeastern, and my BS, that's a Bachelor in Engineering degree actually, from University of Mumbai in India. My research interests, they are more likely including computer architecture, both CPU side, graphic processor side, runtimes and schedulers for GPUs, some application development for modern accelerators, performance modeling, simulation, and as well as some low-power ARM architecture stuff. So, going ahead. So, for the outline of the talk, brief introduction, give you some background of the term. What's the problem? I'll explain that. I'll talk about the 2 levels of concurrency that I'm introducing in my talk. And then supporting research and future work that we are planning to do in this field, and end up with the summary of what we have done till now. So let's look at some parallelism through the generations, what has come through in computer engineering and processor development. Let's go back, put ourselves in 99, 2000 ages, where we had a Pentium 4, a single core device, had multi-programming in it. Surely you could run multiple programs at the same time. But were they running all at the same time on this? No, they were time sliced. There were many different things that went into them to get it done. The technology went down on CPUs, got itself bettered, and we came out to a multi-core era. We put 2 cores, 4, 8, 16, 64 today, also available on a single core, and many more. So we came out to a multi-core era in which we had multi-threading. So now we have multiple threads working together. Earlier we had multi-threading, but they used to work on a cooperative basis. Now, we also have multi-programming, which is always there. We expose something like SIMD parallelism. And to extract more ILP, or what they call instruction level parallelism on a GPU, on a CPU, we had multiple execution units. So that's where we stand today, looking at Core i7s and everything with 4 cores and 8 cores and being happy. But there was something that went on the other side of the fence. It's called the accelerator. Our most friendly accelerator that we have used over time is the DSP. Is signal processing acceleration, high performance math operations on that, and excellent double precision support. Their jobs was to do signal processing applications at double precision support. Later our dataset group, our flexibility we wanted to have more flexibility. We went to FPGAs for their acceleration also. We used specialized kernels on FPGAs to fast forward our problems, or to use pipeline structures like video processing also to go through these. And then come the big boys. They came in the years earlier, used for gaming, till the time in 2005, graphic processors were begun to be used as full-fledged compute devices by NVIDIA. They introduced a new architecture called CUDA, Compute Unified Device Architecture, which used the GPU for computation. AMD joined the race, with OpenCL being on there. And the latest guy on this thing is the Intel's Mike or Xeon Phi processor. It's a co-processor with many cores on it. Basic job, SIMD processing, excellent for data level parallelism. They have thousands of cores and can do brilliant things in a single moment. So, our job is right here on GPUs. My expertise a bit more is on GPUs. So what is a GPU? Looking at the left, sorry for the so good lettering here. So, a GPU consists of some some command processors which dispatch its work. The major part comes here, where there are multiple, something called as a compute unit or a CU. Each CU has got many cores in it. I'll come back to it. It has a shared L2 cache for all the CUs, and every CU has its own L1 cache. Let's say it here. Let's look at what the compute unit looks like in itself. For AMD, they have 64 small cores in one compute unit, divided into 4 sets. Each set is called a SIMD lane. Looking at it, they have a L1 cache, which is private to the compute unit. And as you see, the L2 is shared. What's the most interesting thing is that different flavors of GPUs, low-end, high-end, have different number of compute units. As low as 4 to as high as 44. So the compute power here is extremely different. The way it can scale up is amazing. Now let's go to how to program these guys. How do you get to program them in this environment? I talked about NVIDIA CUDA. CUDA is a programming framework that was developed especially for NVIDIA guys. It's a proprietary to NVIDIA thing. They don't release it for others and don't support it. You can do a C, C++ based coding with their API. It's very easy. People who know C, C++ will adapt to it very easily. The key feature of CUDA has been over the ages its support for different libraries. They have provided mathematical computation libraries from all different domains, be it signal processing, be it fluid dynamics, be it machine learning. They have an acceleration library present. NVIDIA has invested a lot in that. The reason for it is the flexibility. Because it's their own, they can match the device for CUDA or CUDA for the device. They can play with it. That's not the case when OpenCL came up. OpenCL is a consortium. Many vendors came up to form a standard called OpenCL for programming the GPUs and many core accelerators. Beautiful thing of OpenCL, it's supported on CPUs, GPUs, FPGAs, and DSPs. They use a C99 based device code generation. You can write, if you know C, you're all golden for that. And C++ based or C based postcode support. And the key feature there is code portability. If you have written code once, we can take it to any of the listed device, compile it, runs really fast. The thing is it performance portable? No, not at all. None of the things will be performance portable. You change the device, things go off. So how is a GPU programmed? Let's look at something. So there are many threads in a GPU. They launch a lot of threads on the GPU. They are also called work items. Let me give you a warning. We are dealing here with my expertise, with my work. I've dealt with AMD and OpenCL, but don't worry. All the things that I tell you can be exactly applied to NVIDIA and CUDA. So we call them work items. NVIDIA calls them threads. Work items are the small threads that are launched. Every thread is performing a function called the kernel that the GPU is meant to do. Everyone is doing the same thing. Okay? These work items are grouped here to form something called as a work group. It's a logical group. And all these work groups form something called as an ND range or an n-dimensional range, which has a size. The size is of the 3 dimensions. Because it was a graphic processor, it has the 3-dimensional support from itself because it came from the graphics domain. X, Y, and Z coordinates had to be represented well. So size of an ND range is nothing else but the number of threads in all the 3 dimensions and their multiplication, X into Y into Z. So if you have a straight array computation, you'll have only the X dimension. If you have a matrix computation, you might have both the dimensions, X and Y component. So how do you start writing a GPU code? You create a context of your execution like it's normal code. You find the GPU devices, then you compile your GPU kernel. You create the data buffers that were required for your computation. You copy them to the GPU side. You execute your GPU kernels on the GPU, and the red part says that this is exclusive activity of the GPU. The green part is that both things can be involved. And copy back the data from the GPU, and your computation is done. So all these steps can be done using API that OpenCL and CUDA provides. So it's an easy computation based. The learning curve can be one month. If you come to me, I can take it to you in 2 weeks. That's fine. So we have seen many people, many codes, last 10 years, GPU's existence. People have had 300x speedups, 250x speedups. An amazing single-threaded codes going to GPUs and performing really well. So, but what's the problem? What happened over these ages? The workload started processing multiple kernels. Now you had give everyone an option, they want everything. Then concurrent execution and flexible scheduling. They said, okay, we have multiple kernels now. We want them all together on the GPU. The GPU was not prepared to have that. Dynamic resource allocation was required because now we want flexible scheduling. We want to give them resources accordingly. There are too many cores which are not utilized sometimes. And the last is everything has to happen at runtime. The user should not know about it. Everything has to be handled underneath. Let's do it under the blanket. Why we reached this problem is because I can give you an example of why. Let's take this back to 2012. A piece of history says that Goldman Sachs, a company in New York City, said we are not going to build any more data centers. So you're going to use the existing GPU, fit more computation in it, do whatever you want to do. We are not going to invest more on that. It's too much cost for energy. So you have to fill the GPU now with concurrent applications and everything. So that's where the problem started, and this things came into picture. That brings us to the first level of concurrency, that's multi-kernel execution. Earlier, traditional single command queue mapping used to be used. that the host, that's a CPU, normal thing, used to have an abstraction called the command queue, which is used to send commands to the GPU. Here we are sending a kernel A and a B. Each kernel used to get the entire GPU for its execution, all its compute units. Once it finishes, the next one used to come. But this was a kind of a not good of a model. Resource utilization suffers. If the one guy doesn't use anything, you're putting many compute units unused. What do we do with it? OpenCL brought something called as multiple command queue mapping, where you could divide the GPU into two sub-devices or many sub-devices, each consisting of different compute units. And you could have command queues mapped to both of them, or for our example. Now these two can start executing at the same time, because you logically partition the GPU. Good utilization, you have two kernels executing at the same time, but the user has to take a decision how many compute units he requires. How will he make the decision if he doesn't know what's underneath? Worse, if you're performing this on a cloud, you don't even know what device it's going to be on. So that brings us to one of our important contributions, that's adaptive spatial partitioning of the GPU. So what we do is that we assign two properties to the sub-device. One is a fixed, one is adaptive. The ND range of the kernel on that sub-device, which has adaptive properties called adaptive ND range, the other one is the fixed ND range. So the adaptive ND ranges are managed beautifully using a partitioning handler, which has three stages. The dispatcher, which manages the new ND ranges which are coming to the GPU. Those are sent to something called as a load balancer, which then detects if there are multiple adaptive ND ranges. It looks at their size, compares their size, and then with a ratio forms the perfect partitioning of the GPU that can be done. Once that is decided, it starts scheduling the GPU. It starts sending the kernels to the GPU devices itself. And if you have a fixed partition guide, the ND range scheduler will make sure that you are given the fixed amount of resources and you start executing. All these things are a two-layer execution thing, one in the host runtime and halfway in the hardware scheduling. So how does it work? Let's take a case study here. We have one ND range which came into the thing. I don't know if you can see in the back if there's a color here, 22, with the blue color. According to the computation, it had 22 compute units got assigned to it. Another adaptive ND range came through, and the handler decided that the division for 32 compute unit GPU was going to be 20 and 12. The 12 was going to be given to the next guy. Now what about the two that were already given to the earlier one? So we lock them. We do not submit any more workload to them. Allow them to complete whatever was submitted, and then assign it to this guy. This is just a case study of one example with two kernels. There can be many. There can be 10. So there's a constant exchange that can get on happening. And this way, the adaptive ND ranges can just grow and fold back, adapting to the different guys in the GPU at that moment. So what do we see as a performance? See, for the performance, we had a strategy. We made some in-house applications right now. We have more benchmark stuff also. The applications were from communication background, a big data computing, textures, search applications, and a matrix equation solvers with multiple kernels in them. So we had three schemes: the full fixed scheme, in which everyone was given equal resources, fixed, managed; full adaptive, leave it to the runtime, let it decide what's to be done; and the hybrid, where some of the kernels were fixed and some were adaptive. We see that the fully adaptive was always better than the fixed guy. Only for the cases it failed was the big data computation, where the one kernel was huge, the second kernel was tiny, the second guy was starving. So that's where the problem started coming in. But the hybrid, in all the cases, performed really well. But the hybrid is a level where your expertise has to come in of how many to give to the fixed. So we fix this problem by we can convert a fixed guy to an adaptive and an adaptive to a fixed in the runtime if we detect a problem. If a kernel is running for too long, occupying too many resources, we take a decision right now in the runtime. And a fun picture of how does the thing work on the real. This is the COM device. This application has 4 kernels. Everyone has, so the computation is set up in this way that they end up having same number of kernels at the end. So as you see, first ND range comes up, it takes many compute units, but as they all come in, this starts dropping. everyone starts gaining, and they reach an equilibrium where they all have equal distribution. And then when one guy completes, his resources start getting given up to some other guys. So it's a good way of adapting. So we saw that performance is good. Now let us think if we have analyzed and understood it. Workloads possess multiple kernels. Yeah, we gave support for that. Concurrent execution. Yeah, we gave support for that. Dynamic allocation. Yep. Runtime. Yes, sure. Then someone else raised the hand again. What about multiple application context? This is only for one application. What about if there are two? If there are three more applications? Imagine yourself in a data center. You have one server, one GPU, but there are 200 users. How are you going to put their computations? Maybe one application with 10 kernels didn't have that much big computations in any kernel. So still the half of the GPU was lying alone. And we saw that happening in the celebrated benchmark suites for GPUs like Rodinia and Parboil. Many a times we saw 40% of the GPU was lying idle for these computations with many kernels in it. So that brought us to the second level of concurrency, that was multi-context execution. What is a GPU application context? It consists of two parts. One is the memory objects, the data buffers that belong to the context, shared memory pointers, textures that are involved, images that are involved. And mind you, textures and images are actually a data object in both CUDA as well as OpenCL and the GPU language. Yeah, program objects like the kernel instructions, the kernel binary itself, the command queues that are described here, the sub-devices that were created, and the kernel resources that are required. So this form a GPU context. But there are some problems when you want to put many contexts together. That's one of the challenges here. The first thing is the virtual address space isolation. Imagine yourself, if you have taken a basic OS class in your undergrad anytime, there is something called as a virtual address space for every process that runs on a machine. It has its own set of address locations. Now, if you put two of them in the same device, you have to make sure that two contexts do not read each other's addresses. And that's tough. That's going to be fun. The next is global memory management. You have 4 contexts, but my dear GPU has only 1 GB of memory on it. How do I manage that? I don't want one context to be left out just because you cannot get space, but there is space on the computation side, but just not on the memory side. So I've had to adjust that. Compute resource allocation. The context also have to grow and shrink with their resources, adapting to guys around them. And all this has to be done with the GPU in charge as well as the CPU in charge. So we come to the first thing, virtual address space isolation. If you take yourself back to the slide 3 or 4, I said that L2 cache on the GPU is shared. If we put some compute units to one context, some to other, the L1 is not going to be a problem. It's going to be private. The context is going to manage it there. But on L2, they are shared. Imagine two contexts asking for the same address name, address ID in the L2 cache. Which one is the correct one? We cannot say that because the caches are virtually attacked, right? So we have to add something like the 2-bit CID, that is the context ID, to a tag in the L2 cache as well as the TLB. There's a translation look-aside buffer, which is placed beneath the L2 cache in GPUs, which converts the virtual addresses to physical addresses. People who are used to CPUs, warning, TLBs are present. The physical address translation in CPUs happens above the shared caches, not below. So we have a transparent memory management mechanism also in place for a global memory management problem. I'll explain how it works with one use case here of one context with 4 kernels. These 3 are its arguments, or called the data buffers that it's going to use. And you might have seen that this is the command queues that we got created. K1, K2, K3 are in series because they have a data dependency. K4 is not. So it's on a separate command queue and can execute in parallel. So I have timestamp T0 here. This is the state of the GPU and the CPU, both sides. At T1, we start sending in all these guys which are to be used by the K1 and K4. The next one, K4 and K1 start executing their buffers present. They start modifying them. Next stage, we detect that K2 is executing now, but K3 is next. What's missing for K3 is the D buffer. Now we bring it. And at the same time, we are done with the use of A and E. We're sending them back. At that stage, the next stage, K3 executes, required buffers in, B is going back. And once all of it's done, we bring C and D back. And the last stage, we have every compute is done, everything is finished. And the buffers are back in D. What we saw was we overlapped our computation with communication very efficiently. We did not let, okay, we want some buffers, send them then do the computation, send them back again. So we didn't do these things. Imagine yourself that you have this one context and now you have 4 of them. So every one of them will have a kernel which will have its own requirements, but will take up some space on this GPU memory, which is limited. So by sending these buffers out and in, we can make space for others to execute among them. So this is all controlled in the runtime, and the user has no idea about it. So the resource allocation and remapping. We start we begin every of our contexts with like 25, 50, or 75% of its resources, or 100%. Its allocation is based on the priority. The remapping scheme is based on likely of these concepts. High priority contexts can gain the CUs, low priority can lose them, but can also gain if there's nothing else remaining to compute. And the context switch will be only done when resources cannot be released efficiently. So the mechanism works this way. It checks for unused compute units, assigns them to the high priority guys. Then we check again if the high priority guys have got what they wanted. If yes, we assign the remaining to the low priority. If not, then we have to go to the context switch policy, and we have to do a context switch. Sometimes a context switch is more efficient, but sometimes it's not. It's costly because it's not a CPU, it's a GPU. You're talking about 2,000 threads which have to be taken out for many times, and that's going to be costly. For our evaluation, we created a mixes of application with different resource allocations. So one format of mix was the characteristic based, but the characteristic of each mix was different. It was either memory bound, compute bound, or compute heavy and memory heavy. And the other was shared allocation based, in which we increased the size of the contexts that were present in the mix. We used the baseline. The baseline for our computation was that when the contexts are executed sequentially, like if in SHR there are 2 contexts, the baseline was the total time taken for first and the second, and then that's the thing. But our execution was concurrent. So let's see what we got as a speed up here. A good trend, the y-axis, the secondary y is showing the speed up. We are also looking at compute unit utilization red bars, and the ACE unit is the units which are present on AMD GPUs which schedule kernels. So what we see, an average speed up of 1.5x. A compute unit utilization average improves by 18%. Here for CHR1 is 20, SHR2 greater than 20%. And the speed up will reduce as you increase the number of contexts. The speed up can also hit yourself if you're having a different feeling. CHR1 had a lot of memory accesses. That created a bottleneck. All of his contexts were like trying to get to the memory and getting stalled. And that's where we started facing a bit of problems. So who to couple with is also one question that has to be answered. Then the global memory management. We did this by studying the entire global memory usage over time for different combinations as we increase the number of contexts. Interesting thing I can show you, sorry for the graphic there, but there's one application here, BP, which was present with 3 contexts in this scenario and with 2 contexts in this scenario. The way the data started moving for the same context was different. It was much more aggressive here, and it was very much leisurely because it had a lot of free memory, which it could take for other buffers and can manage not to be rushing into it. And the last one here, this guy, SHR4, has 4 concurrent contexts running. And we can have a look at its burstiness, in which the data gets sent out, sent in, and it gets managed when all the contexts are working together. At the end, it starts falling because the computation ends, and we send the data out. Is everything hunky-dory for us? Everything is happy? No, it's not. L2 caches are still shared. Many contexts are still attacking them. So their efficiency over the blue guy was sequential, red was multi-context. The hit rate reduced. Why? Imagine yourself. You are one context. You had one context having this one cache line. Other contexts came in, couldn't find a space, but had to be located at that cache line. So this guy evicted this guy. The first context cache line with its own. Now the original context came in looking for this. Didn't find it. So this is called the conflict miss, an interference. So the amount of conflicts misses that we've seen in this entire scenario are about 30 to 38% actually of all the L2 misses. This strategy has to be taken care of. What we can think of is a physical tagging, physical translation. So you use a physical tag for L2 caches and then form a different cache partitioning policy. That's something that we do in the future. So, bringing out to a steady end, what are the supporting work that I've done with this? For all this purpose, we are using a simulator that we have published a lot of papers on. It's accepted by the industry, and AMD also has validated it with us. It supports x86 modules and GPU cycle level simulations. So I put extensions on it to support our scheme here, as well as we have evaluated graphics and compute interoperability of how they work with each other, and looked at OpenCL and CUDA's new features, and have created a new benchmark suite called NewPar for kind of looking at different features and hardware features as well as software features that came to new GPUs, and there weren't benchmarks to evaluate it. All these are papers that have been published. All the two concurrency level chapters are also papers. And for the future work, I'm trying to detect the behavior phases in GPU applications on the go. We use these phases for effective partitioning. We're going to use some machine learning techniques. And we want to implement architecture support to do this on the GPU itself. As I said, we want to explore with the address space isolation with physical tagged caches and utility-based cache partitioning. With this, I will summarize the talk. We have identified the flexibility requirements, detected the levels of concurrency, had adaptive spatial partitioning for kernel level, and have had dynamic resource and memory management for context level concurrency. And all these features are implemented in architecture and the runtime. The user was oblivious to this. It's a good thing. The user has his own problems to solve. We are letting him do it efficiently. With that, I thank you all for listening to me, and NEPSSS for giving me this opportunity. I'm up for questions. Thanks.
The second one is right on time as well. So, excellent. Yeah, go.
So I have actually two questions. So I just want to make sure that when you're timing, with your timing, your scheduler is also involved in that timing, right?
Yes. The scheduler is parallelly working in this.
It's in the cycle.
Yeah, it's in the cycle. Yeah. As the GPU is working, the scheduler is also doing this job.
So I'm a little surprised when you put what was the maximum number of contexts that you?
We put for evaluation we put 4.
4. Okay.
Yeah, but as you can increase the bitness of the context ID, go to 8, 16. Just one bit addition, you can get them.
I would expect that increasing context there would be a sort of decaying curve.
Yes, there will be a decay.
Because of the communication.
Yeah, there will be a decaying curve, but then it brings out. It depends on the context. Here we wanted to exercise the entire system. And then if you are having multiple contexts, one context is not that heavy, then perhaps you can still suffice. Now it depends on when do you want to have it. So it's a server level strategy perhaps that an admin can use with the runtime guys, and in a words, vice versa. So priority based can be a good billing scheme for the user who's using maybe a cloud server or something like that.
Yeah, I mean, if you do priority, then you don't have concurrent 4.
Absolutely.
So concurrent 8, you have concurrent 3, concurrent 4, right?
Yes,
yeah,
yes,
so
we can try and maintain it.
It goes to that.
Yeah,
sure.
Any other questions?
Sorry, I have one.
Oh, yeah, sure.
So on slide 12, by the way, see when you number your slides, then people can say this. So you made the comment, this is where you were showing the results of the hybrid technique versus the other two. And you said something of, how do you know if one kernel is using too much? Did you set a threshold, or is there an absolute?
Yes, the kernel, so the runtime and the hardware can program it, the driver can program it in a way that we can start detecting the usage of a particular kernel and how many compute units it belongs to by looking at certain number of registers. And if we find that from the start to a particular time slot, we can experiment on what time slot to give that. Right now, we are doing somewhere around 1 million to 5 million cycles.
But if somebody is using an arbitrary application that you've never seen before, how do you know what is too much? That's what I'm trying to understand. How do you if you don't know what it is and they put it on there, maybe that's just like that one example you gave, that's just the way it is.
Yeah, to precisely point out your problem, there is a kind of applications that exist in GPUs called the persistent kernels, which never leave the GPU, they're just there. They don't even leave the GP. In that cases, we always try to reduce to be flip the way they are from fixed to adaptive, and we try to get them to a minimum level of working. When do we do it? That's the question. We have right now a fixed arbitrary threshold, but that we have decided over experimentation,
got it.
but that can be converted.
Got it. Okay, thank you.
Okay, so I think we'll wrap up. I want to thank everyone for coming. I think this was a great success.